Section 3.2, Polynomial Functions and Their Graphs. A polynomial function of degree n is given by p of x, where all the exponents are whole numbers and a sub n is not equal to 0. A sub 0, a sub 1, and all the way through a sub n are called coefficients of the polynomial, and a sub 0 is the constant coefficient or the constant term. And the term a sub n x to the n is the leading term, where a sub n is the leading coefficient. So here's an example. Given this polynomial p of x equals 4x minus 7, the degree is 1, the leading term is 4x, the leading coefficient is 4, and the constant term is negative 7. P of x equals x cubed plus x has a degree of 3, leading term of x cubed, leading coefficient of 1, and constant term is 0 because there is no constant term here. P of x equals 2x to the 7th plus 3x squared minus 10 has a degree of 7, leading term of 2x to the 7th power, leading coefficient of 2, and the constant term of negative 10. And P of x equals x cubed minus 1 minus 4x to the 5th plus 2x. We need to first write a polynomial in descending order, and we can see that the degree is 5, and the leading term is negative 4x to the 5th. The leading coefficient is negative 4, and the constant term is negative 1. Here are the graph of some basic polynomial functions. P of x equals x is a straight line going through the origin with the slope of 1. P of x equals x squared, which is a parabola opening upward. P of x equals x cubed. P of x equals x to the 4th. And P of x equals x to the 5th. So using these basic graphs, we can use transformation to graph any of the polynomials of this standard form. So for this example, given f of x equals x minus 3 squared plus 1, we can use transformation to graph this. The basic graph is f sub 1 of x, which is x squared, and here's the graph of x squared. Now the first transformation is x minus 3 squared, or in other words, 3 units to the right. So the graph will be shifted right 3 units. And the next transformation that gets us f of x is adding 1 to the previous transformation, which is basically 1 unit shifted up. And this is the final graph. Graph of functions in general may have breaks or holes. However, polynomial functions are continuous functions. That is, there are no breaks or holes in a graph of polynomial function. The graph of polynomial functions consists of a smooth and continuous curve. So for example, in this graph, we can see a continuous function, but it's not smooth. We have a corner and a cusp, so this is not a polynomial. We can see this graph is smooth and continuous, therefore it is a polynomial. And this one is also continuous and smooth, so it is a polynomial. The end behavior of a graph of a polynomial function is very important to us. We can use the end behavior to graph a polynomial and see how it behaves towards the end as x goes to negative infinity or positive infinity. So given this polynomial function, if degree n is even and the leading coefficient of the polynomial is positive, as x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, y approaches positive infinity also. If degree n is even, but the leading coefficient is negative this time, as x approaches negative infinity or positive infinity, y will approach negative infinity. And if the n is odd and the leading coefficient is positive, as x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches positive infinity. And if n is odd and the leading coefficient is negative, as x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, y approaches negative infinity. We can see that for an even degree with a positive leading coefficient, the graph behaves like an upward parabola. And for an even degree with a negative coefficient, the graph behaves like a downward parabola. For an odd degree with a positive leading coefficient, the graph behaves like an x cubed. And for an odd degree with a negative coefficient, the graph behaves like a reflected x cubed into the x-axis. So here are some examples. Given this polynomial f of x equals 3x to the 7th plus 4x cubed minus 1, the degree is odd and the leading coefficient is positive. So end behavior is, as x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches positive infinity. G of x equals negative x to the 9th plus 3x to the 4th plus 7 has an odd degree, and the leading coefficient is negative. So as x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, y approaches negative infinity. H of x equals negative x to the 8th plus 4x to the 3rd minus 12. Degree is even and the leading coefficient is negative. So as x approaches positive infinity or negative infinity, y will approach negative infinity. And for p of x equals 12x to the 100th plus 3x to the 57th minus 9, degree is even, leading coefficient is positive. So y approaches positive infinity as x approaches negative or positive infinity. Let's talk about zeros of polynomials. If p is a polynomial function, then c is called a zero or root of a polynomial function if p of c equals 0. In other words, zeros are the solutions of p of x equals 0. Given a polynomial function p and real zero c, the following are equivalent. C is a zero of p, or x equals c is a solution of the equation p of x equals 0, or x minus c is a factor of p of x, or c is an x-intercept of the graph of p. So given this polynomial function x cubed plus x squared minus 6x, we want to find the real zeros of the polynomial. So to do that, first we need to factor p of x. So we get x times x plus 3 times x minus 2. And so either x is 0 or x is negative 3 or x is 2. So zeros are 0, negative 3, and 2. And if you're asked to solve this equation, well, this is p of x equals 0. Solutions would be, again, x equals 0, negative 3, and 2. And if you're asked to find x-intercepts, well, x-intercepts are 0, negative 3, and 2. So what is intermediate value theorem for polynomials? If p is a polynomial function, and p of a and p of b have opposite signs, then there exists at least one value c between a and b for which p of c equals 0. So we can see on this graph, if p of a is negative and p of b is positive, or vice versa, there exists a c in between where p of c equals 0, because graphs of polynomials are smooth, continuous curves. What is multiplicity? If c is a 0 of p and the corresponding factor x minus c occurs exactly m times in the factorization of p, that is x minus c to the m, then we say that c is a 0 of multiplicity m. Why is this important to us? Well, when we're graphing a polynomial, the graph of the polynomial behaves in a specific way at zeros with different multiplicities. If m is odd and greater than 1, the graph makes a squiggly shape at that 0. We call it an inflection point. And if m is even and greater than 1, then the graph bounces off the x-axis at that 0, which we call it a touch. So here is an example that we want to find zeros of the polynomial and sketch the graph of the polynomial. So first, we factor the polynomial and get x times x minus 3 times x plus 1, and we can find the zeros to be 0, or 3, or negative 1. Each of these zeros have a multiplicity of 1, so we plot those x-intercepts or zeros on the plane. Since the degree is odd and the leading coefficient is positive, we can find the end behavior of the graph. That is, as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches negative infinity. So we get this graph. Here are some facts about polynomials. Complex roots of polynomials come in pairs. That is, if a plus bi is a root, then the conjugate a minus bi is another root. A polynomial of degree n has n minus 2k real roots, where the other 2k roots are complex roots. So for example, if the degree is 6, there are 6 roots. If there is one complex root, the conjugate is another complex root, therefore there are 2 complex roots. And so of those 6 roots, if 2 of them are complex, the other 4 could be real. A polynomial of degree n has n minus 2k increasing or decreasing intervals. And a polynomial of degree n has n minus 2k minus 1 local extremum. So let's sketch the graph of this f of x. First, we want to find the zeros. So we have 0 with multiplicity 3, and because it's greater than 1 and it's odd, it's an inflection. We have 2 with multiplicity 2, so there should be a touch. We have negative 2 with multiplicity of 1, so it goes straight through because it's not greater than 1. And negative 3 with multiplicity 1, which should go straight through since the multiplicity is not greater than 1. Leading term is found by multiplying the leading term of each of those factors. So 0.5 x cubed times x squared times x is 0.5 x to the 7th, where the degree is odd and the leading coefficient is positive. So the end behavior would be as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches negative infinity. So if we plot the x-intercepts or zeros on the plane, and given the end behavior and the multiplicity and how the graph behaves around those zeros, we can see that we will have a touch at 2, and since as x approaches infinity, y approaches infinity, the touch should be above the x-axis. There will be an inflection at 0 since the multiplicity is 3. At negative 2, the graph will go straight through negative 2. And at negative 3, the graph will go straight through negative 3. And it goes to negative infinity as x approaches negative infinity. So we should have this graph with local maximum and minimum as shown.